So in today's class, believe it or not, we are towards the end of this course, wherein we are going to talk about position control based on semi-autonomous autopilot. This semi-autonomous autopilot is implemented in the drones that you work with, maybe a small $10 drone or $20 drone. What you have is you have the joystick, and you actually have that drone fly forward, backward by the switching of the joysticks. But the semi-autonomous means the leveling, roll control, and pitch control is done by the internal flight control software, but the position control forward or backward is done externally. And in the last class, I gave you a very simple algorithm to achieve the position control. So let me give you some more details, the mathematical details on those algorithms. And then I would actually show you the MATLAB script that would allow you to do the position control based on semi-autonomous autopilot. So first thing, what we are going to do is we are going to talk about what are we going to study. So first, we will formulate the position control problem as a mathematical equation. And clearly, many a times, the practical airframes, they are significantly different than the designed airframes, because the payloads can shift, because the manufacturing may cause some errors, or once you assemble the airframe, the tolerances affect the dynamic performance. So many a times, even though you start with a design, even if you start with a model based design, then after experimentation, you have to fine tune that model. You have to fine tune your control algorithm. Then we will talk about the position controller design. And at the end, we will talk about the simulation. And we'll end this today's lesson with some experiment or some MATLAB exercises. And if you have any questions related to the labs that you're working on or the Mambo issues, that I would be happy to help. So if you look at, this is the hierarchy of the quadcopter control. If you are going to use a semi-autonomous control, so in semi-autonomous control, what you have is, it's called SAA, which is semi-autonomous autopilot, wherein the motor control and the attitude control, which is roll, pitch, and yaw, is handled by the quadcopter, and the position inputs are given by the user, like you go to the position X, Y, or follow certain track. In the case of fully autonomous, the position input and the waypoints and the path is provided by the autopilot. And if you look at it, initially the critical part is to have the semi-autonomous flight working, and then gradually you can build on top of it. So usually the flight controls that you see, there are a lot of flight control boards that you can get. They are based on the semi-autonomous control, and this is not difficult to implement. As a matter of fact, once you implement roll, pitch, and yaw control, pretty much your Mambo is semi-autonomously controlled. These are the different autopilots that are available in commercial market. So they go all the way from hobby grade all the way to some commercial grade. Some are open source, some are closed source. And if you go to the companies like Rockwell Collins, they specialize in developing the aviation software and autopilots. So most of the avionics systems in Boeing are made by Rockwell Collins, which is now Collins Aerospace. So typically, if you have a semi-autonomous control, you are going to have a stabilization mode. You are going to have an altitude hold mode that put it at constant Z, or you can have a loiter mode, which means perform a special maneuver like loitering, circling, that type of stuff. So how would you do a semi-autonomous control? So think about, you have a joystick. and you have this internal flight control loop that basically controls the altitude model and attitude model. So you have the dynamics that is implemented inside, and the input for X and Y position and Z position is given up by the joystick. Now, how does this formulation translate into the motor control? For a quadcopter, it's an under actuated system, which means even though 6 degrees of freedom, we have only 4 actuators. So what we do is we convert those into 3 channels. You have an altitude channel, you have a yaw channel, and you have a horizontal position channel. And clearly, depending upon what quadcopter you use, the motor mixing algorithm would change. If you have an X type of configuration, the motor mixing changes. If you have a plus type of configuration, the motor mixing changes. Instead of quadcopter, if you have a hexacopter or an octocopter, the motor mixing changes. So assuming that you have a 3-channel control, how would you control those 3 channels based on a very, very simple sort of PID type of control? So what you have is, you have these gains. These are the controller gains that are shown over here. And these controller gains are utilized to control the approximate dynamics of the quadcopter. Now, once again, let me repeat. The original quadcopter dynamics is highly nonlinear. But since we have this highly nonlinear system running at or sampled at very high update rate, we can work with a linear approximation and still be able to control the quadcopter with the PID loops. But for the stabilization, the inner PID loops need to run at a very, very high speed, and the actuators should be able to respond to that high speeds. Because what may happen is, even though your control loop is running very fast, but if your actuator, for example, motor speed, is not able to change very quickly, your controller will not work. So what you want to do is, you want to match these two. The other thing, you also have sensors. Many a times, the data coming from sensors is at much lower rate than your PID control loop. So what you want to do is, you want to do the rate adjust. What that means is, if your data coming from sensor is coming at 50 hertz, but the data that is the autopilot is running is at 100 hertz, then what you want to do is, you want to interpolate the incoming data in such a way that you have an approximate value in between those 2 data points. So even though your sensor values are coming to you at 50 hertz, what you do is, you design some kind of an interpolation algorithm and get that data converted into 100 hertz. And that is implemented in Mambo, and I will show you, because the data that is coming from the vision system is coming at a very slow update rate. With that data rate, the autopilot cannot operate. Autopilot is going to run at much higher rate. So basically, the vision-based data that is coming in need to be upscaled so that the autopilot can use it, which is something similar. I don't know if you have seen those dongles that take 1080p video and convert that into 4K. But where do we lose? We lose basically in the computation cost and update power and the power required. So all those things you will have to manage. So the key point in this slide is, you have basically altitude control channel, which is the Z axis. You have the yaw control channel, and you have the horizontal position channel. Now, some of you may ask me, why only 3? Because please try to understand, with these 3, if you have the inner stabilization working on roll and pitch, you would be able to control your quadcopter very easily. So if you want your quadcopter to go in certain position, you change the yaw and have that quadcopter go in that particular direction. Now, these equations that you see over here are the simple linearized equation from those complex nonlinear dynamics. And these equations, they run at very fast, which means these equations are solved numerically 100 times a second based on the incoming data. That's why the position controls, they would actually work. Now, this is the mathematical formulation. So mathematically, what does position control look like? Position control look like is like you have a reference trajectory that you can split into two parts, a desired position and a desired orientation. So what you do is you actually control, you have actual position and you have the desired position, you form the error and your controller should minimize the error in between. So basically that norm or the difference is somehow should go to zero. Same thing should happen for the altitude. So this is the mathematical expression that describes the controller effort. Now, what is system identification and how do we do system identification? System identification is nothing but determination of system parameters based on the experimental data. And there are some simple experiments that you can perform and get some data from your frame, and that could be fed into the quad, into some type of algorithm or some type of a toolbox like MATLAB that is used over here. And that will give you the matrices that describe the behavior of that system. So what I mean by that, for an example, if you have a spring mass damper system, and this needs a little bit discussion. So what so imagine that you have a spring mass damper system, spring mass and damper system. So what you have is you have M in kilograms, you have C in Newton meter per second, and then you have K, which is Newton per meter. So you have K, which is stiffness, you have C, which is damping, and you have M, which is mass. The differential equation of motion is force is equal to mass times acceleration. So when you plug in all these values, your equation is going to look like mx double dot plus cx dot plus kx is equal to 0. I'm going to divide the left hand side and right hand side by m. So when I divide everything by m, this equation becomes plus k by m x is equal to 0. And then I'm going to define k by m as something like called omega n square. Just I'm going to define this. K by m is equal to omega n square. And I'm going to define c by m as 2 zeta omega n. And this is just I'm defining. And when I rewrite this equation is going to become 2 x dot plus omega n square x is equal to 0. Now please try to understand what I did. Understand that if I don't know value of k, if I don't know value of c, if I don't know value of m, how many unknowns do I have? I have 3 unknowns. Are m, c, and k. 3. But what I did, I represented those 3 unknowns in terms of some ratios. I represent those 3 unknowns in terms of some ratios. And right now, the same equation only has 2 unknowns. One is zeta and other one is omega n. So what it means, if somehow I can find out zeta and omega n, I know what the system parameters are. And determination of zeta and omega n experimentally, so experimentally is nothing but system ID or system identification. So how would you know the system identification? The easiest thing to do is pull this mass and let it go. You would observe that this system is going to go like oscillation, something like this. And what you do is you find out the logarithmic decrement. So what you do is you find out this value x1, you find out this value x2, and ratio of x1 by x2 actually is 1 divided by 2 zeta omega n. That gives you one equation. Then what you do is you find out the frequency of vibration. So this is the period of vibration. I'm going to call this TD. From TD, you can find out omega D. Omega D is 2 pi divided by TD. And 2 pi divided by TD is 1 minus zeta square omega n. So now what you have is you have two equations and you have two unknowns. So with these two equations and two unknowns, you can find out value of zeta and you can find out value of omega n. Everyone understood this? So what it means is by performing some experiments on a simple system like spring, mass, and damper, you can identify the dominant characteristics. And once you know that, basically this equation is completely known. What that means is you have the equation for the dynamics of the system. So think about it like this. You started where you did not know anything about the system. You performed some experiments and you got the information that was missing. Now you know everything about the system and you can predict how the system would behave at any time t. So for an example, if this experiment was performed for say 5 seconds, you may not have full set of data, but with this 5 seconds of data, you can find out the zeta and find out omega n, and you can predict what would be the amplitude after 10 seconds, what would be the amplitude after 100 seconds, when would system become stable, how much decay the system would have, and so on and so forth. Same thing can be done for system identification, wherein what you do is you capture this experimental data, you feed that data to either a software or some type of mathematical algorithm. There are a lot of mathematical algorithms that would do system identification. You can do dynamic decomposition, you can do mode analysis, and then or you can use MATLAB, you can do the system ID in state space, transfer functions, so on. And finally, what you do is you get this system model. Once you have this system model, what you do is you test your system model by performing the repeated experiments under varying conditions. So, for example, you get the data and you give it a step input and you capture the system dynamics. Then predict, if I change that step input to a ramp input, how would the system behave? From mathematical analysis, you predict the system response to ramp input. Give the same ramp input to the actual system and see how well the system actual response matches with the predicted response. And this cycle would continue as long as you have completed all the scope of operation. So for an example, system could be subjected to sinusoidal input. System could be subjected to random input. System could be subjected to ramp input. So what you do is, once you validate for a subset of inputs, based on your confidence, you can predict how the system would behave when it is subjected to stochastic input. So this is the beauty of system identification. And believe it or not, this is very important. Machine learning is one type of system identification. So roots of machine learning, they start with regression and then other lasso and other sparse regression. All those, they are deeply rooted in the basic tools in system identification. The problem with system identification is, think about, as the system becomes more and more and more and more complex. Imagine you have to find out 100 parameters. Imagine you have to find out 200 parameters. Imagine you have to find out 1,000, 2,000, 100,000 parameters. You cannot do that with hand. For that, you have to use computer. And machine learning architectures, they help you to find these different properties. So the weights and the biases in the machine learning, the weights and the biases help you identify the properties of the system. So it's like a system identification. Machine learning is a universal approximation of the system. And again, it actually, with the advances in computer science, with the advances in computational power, the machine learning actually just took off. But it started with the basic concept of system identification. Now, one thing it's very important to understand is, we talked about the linearization. So if you look at the basic machine learning or neural network, basically neuron has a weight and a bias. So basically a single neuron is a linear element. But what happens is, when you combine multiple linear elements and add activation functions. Now this is very important. So for an example, and this is also used in control theory. So for an example, you have a linear element which has some weight and it has some bias. So there are two parameters for each neuron. And you have hundreds of neurons, but you add an activation function which actually modulates how those linear neurons get combined, or how those linear things work. So this cascaded linear chain becomes a nonlinear function. So neural network is able to approximate a nonlinear function because the linear systems are cascaded with activation functions, where sometimes they are active, sometimes they are inactive. So there is basically a famous theorem, a basis of neural network, that talks about the series of linear approximations combined with activation functions can approximate any nonlinear function. That is the crux of neural networks. So now, when you expand that to the control theory, wherein on the right hand side, what you have is a controller implementation. On the left hand side, what you have is an open loop system. With the controller, what you want is, you want to control the behavior of the system. And there are different controller techniques. There is linear technique, nonlinear technique, but system identification becomes an important part, wherein the controller can be tuned in that particular range where the system parameters are expected to vary. And again, what you do is, you perform the same type of experiments to come up with the controller parameters, tune the gains, and basically control the system in those three channels. And there are different techniques for controller design, but at the end, what you have is, you want to make sure that the system that you are going to design is simply stable. And by simply stable, it means that you are able to control the amplitude and how fast the amplitude decays to a particular value. And believe it or not, PID control is nothing but a way of controlling the amplitude and the decay. And believe it, let me give you a simple example. So let's go back to the example that we talked about, that I have this spring mass system, and what I'm going to do is I'm going to add a P and D control. So this is the I'm going to add P and D control. So this P control would look like Kp times X, and this D control would look like Kd times X dot. What I'm going to do is I'm going to add these two controls onto this underlying equation and see what happens. So my original equation is X double dot plus 2 times zeta omega n X dot plus omega n square X is equal to 0. I'm going to add the controller, which has Kd plus omega n square X plus Kp times X is equal to 0. So now my equation will get changed to something like this: 2 zeta omega n plus Kd X dot plus omega n square plus Kp X is equal to 0. So now I want you to tell me what happened from the original equation to the new equation. By adding the controller, I added the amount of damping in the system. Do you agree with me? I don't know if you, so initial equation was something like this: mx double dot plus cx dot plus kx is equal to 0, where C is damping. Do you agree with me that by adding Kd, the effective damping of the system went up, which means the system sort of stabilized? By adding Kp, what I did, I increased the frequency of that system. So basically, by increasing the frequency, what actually is happening is the effective amplitude will be reduced. So the Kp and Kd are actually essentially changing, believe it or not, but the poles of the system. So if you were to find the eigenvalues, Kp and Kd will change system eigenvalues, and stability depends upon eigenvalues. So by changing Kp and Kd, you basically change the poles or the eigenvalues, and that in effect would change the behavior of the system. So that is what is happen. That's what happens. Now, many a times, what you do is you start with an approximate model, and that approximate model could be in the state space, or it could be in the Laplace domain, or it can have, that is what is called transfer function. That's what we discussed in robotics 1 towards the end. So you can have the mathematical model as a transfer function, or you can have a mathematical model in the state space, and then you can design the controller either in state space, or you can design the controller in transfer function model. So again, the final thing here that I want you to look at is by adding the controller gains, the initial system that was unstable is now made stable by tuning the eigenvalues where the system is. So you can add the controller gains and that would affect the eigenvalues. So what are the different models that are used in system identification? So for horizontal channel, what you do is you assume the phi, the psi, which is the yaw channel, is equal to desired channel, and then the rotation matrix about yaw actually becomes a constant matrix, and then the position equation in the transfer function form becomes very simple, which is given over here. And this equation can be used either for simulation or for autopilot implementation. Now, if you want to try the horizontal position control in a state space form, you can still do that. This is the state space equation, and you can implement the controller in the state space form, same KPs and KDs, and you will have a controller equation in the state space form. Now, again, if you want to add PID controllers, the same equation, you would have a KP working on the difference between the positions, KD working on the difference between the velocities, and KI working on the integral of error. The error between the desired position and actual position is E. So you have KP acting on E, KD acting on E dot, and Ki acting on the integral of error. Now, what are the advantages and disadvantages of PID control? PID control is simple to implement, but unfortunately may not work all the time. You need to do a lot of tuning and gain scheduling and gain tuning for PID controller to work. So the idea is, depending upon the maneuvers, the PID gains could be different. But if you have a solid, robust model, then you can actually use some sophisticated techniques rather than PID control to control the behavior of the system. And next part is basically how the simulation works. And I will show this to you with the simulation that we have in our Mambo. So you can have a simulation script, and that simulation script you can run and look at the behavior of the control, and then finally you can use those simulation parameters and actually program the actual hardware. So in this example, this is also available at MATLAB file exchange. This is the AR drone from Parrot. Again, the Simulink hardware-based control can be implemented on AI drone. So you have the Simulink coder that can actually code the firmware of AI drone. But that drone is a big drone, and what I'm going to do is I will show you this process on the Mambo. So we do system identification, we do the control, but please understand the systems that we work with, they are not ideal systems. So there is always going to be noise, there is going to be friction, there will be some modeling uncertainties. So what you have to do is you have to add that in simulation, something like a white noise or some type of a disturbance, and then see how well your simulation works. And more knowledge you have, more information you get about the data that you have, your system model can be further improved. And please try to understand there are two principal philosophies. One is model-based design, wherein you start with a mathematical model, use that model to design, and there is experiment-based design, which means what you do is once you have the system that is built, you perform series of experiments and then refine the underlying model that you have. And what happens is when you go to industry, these two approaches are used simultaneously. You start with an underlying model, design the controller, implement the controller on actual hardware, perform lots and lots and lots of experiments, make sure the controller works, and then move forward. If you think about the aircraft design, there are tons of flight tests are done before the aircraft is deemed fly worthy. So most of the time you do the controller design analysis on computer, then you basically do a small scale prototype, you test it, then build a large scale prototype, test it, refine the controller, and then finally actually deploy it on the commercial hardware. So typical system identification is something like you do the data record, and from the data record, what you do is you do the analysis and then use a particular model, whether a single order system of zeroth order system, first order system, second order system, that describes the behavior of the data, and then use that second order, first order model to test and then modify or improve that model and finally deploy. So what is the summary? So model-based design is becoming very, very important. Model-based design is complemented by experimental design. And finally, when you go to industry, you would be using, depending upon the task, depending upon the outcome, depending upon the time, resources available, you would either use one or two or both. So with that, we have finished chapter 12. And are there any questions? If not, I will actually like to show you a little bit of model-based design on Mambo. And I would be happy to answer any questions that you may have. Any questions from students? If there are no questions, what I'm going to do is let's go to MATLAB. And I will share my MATLAB screen.
Actually, I have a quick question.
Yeah.
What we talked about, like predicting, right, using like the system and the behavior using the formula, doesn't that heavily depend on the initial conditions?
Well, yes. But what you do is, again, it depends upon the initial condition. It also depends upon whether the system is linear or non-linear, because many a times if the system is chaotic, a teeny tiny variation in the linear condition will give you completely different result, something like a butterfly effect. But the assumption is that we start with a linear system. So linear system, even though the initial conditions are different, they are fairly predictable. So we start with a linear plant model, use that, improve on it, and then test that plant model and the controller for variety of initial conditions and make sure that the system is responding the way we want. Okay. So what I want to show you, so these are all the pre-built Simulink blocks that are available for you to run. So you can actually start with Parrot mini drone hover start. You can do Parrot mini drone keyboard start, Parrot mini drone orbit follower, Parrot mini drone waypoint follower. You can start Parrot vision in external mode. You can do Parrot keyboard control. So what I'm going to do is I'm going to start with the Parrot keyboard control, and that is the semi-autonomous control of Parrot drone. So did anyone look at the webinars that I showed in the last class, the MATLAB webinars on? Did anyone try to repeat what he said or what he did in the Simulink? So here, as you can see that you have a keyboard input, and this keyboard input basically gets the data from the keyboard, and then it gets fed with the values. So for an example, if you press A, I think that the drone will go forward. If you press S, let me see, that drone would go backward, something like that. Let me see, what does it say? And you can change it depending upon what input you choose. So you can actually use this for the parrot mini drone control. And then here there is a comparator, and there is here the switcher, and that gets used for parrot mini drone control. And then you don't change this error block. So this is one block that is used for parrot mini drone control. So there is something else that I want to talk about real quick. So what I showed you was the template, and this is the solution. How would that be implemented? So what I want you to do is, I want you to open the template, and then I want you to open the solution. And you can open both at the same time. But one is just an SLK Simulink file, and the other one is actually the whole project. And once I show you these two side by side, you will understand the control logic that is implemented. And you don't have to run this as a project. You can just run that as a Simulink file. So here, now you will notice there will be two files. So there is this flight control system. I will show you what happens in the flight control system. Open this up. What you have here is you have this image processing system. What this does, it gets the RGB data, and this RGB data needs to be converted into some type of vision-based algorithm, and then apply, you can give it a flag. But one thing I want you to understand, that this RGB data, where did it go? So main models, RGB data, the vision sensor is running slowly than the actual control loop. So you have this rate management box. So you'll see here is rate transition that would actually take this low frequency image data and send it or oversample it or interpolate it and send it. Yeah. Ooh. What do you mean? I'm not sure. Oh, you are sharing screen. It says sharing screen. Okay. Okay. Thank you. So this is the vision based. Oh, screen stop. Okay. So basically what you have is you have this incoming image data that you have rate transition, and that actually gets converted to the high dimensional data that gets fed into controller logic. And then one thing I want you to know, that there is this optical flow that actually comes into this block, and there is this optical flow algorithm. So what you have is you have all the sensor data coming in, that gives you the estimated outputs, and those estimates go out from this flight control system. So you can actually get these estimates to the workspace. So what we talked about is actually implemented in here. So the position control. Okay. So one thing I want to show you, and it's like when you play with this system, you will know more. So please try to run these sample codes. Now, in this code, what you do is, this is sort of the system identification for the Parrot mini drones. So basically what you can do is, you can actually get the vision data. This vision data gets converted to RGB. This RGB data gets fed, and then basically what you do is, you can use this for detecting particular color. And then based on that, what you can do is, based on that color, you can actually tune the motors. So if you want to implement maybe line following, what you can do is, you can go here and then take this image data and implement your image processing algorithm over here and do the line following. So what I want to do is, I just want to run this code real quick and show you the output. But please understand, this is not a spectator sport. So I would strongly recommend that you do these activities so that, okay. What you do is, you want to run this in extern mode. And you can actually double click this video viewer, and you will actually see on the screen what the drone sees. I'll show you in just a second what happens. So check this out. See this? That's my name. And the motor starts spinning because it's detecting the red color, and then it should stop. I don't know if online students can see this. I guess I can start the video. And I want you to see. So this is parrot member going on to this. Now what is happening, it's actually seeing in red, but because of the thresholding, the way I have done, the red is appearing white. So that is because of the thresholding that is done. So what I would encourage you all to do is, there are lots of exercises inside this Parrot mini drone. Please play with those, and that will give you more confidence on building some of the applications on your own. So that's it for today. I'm gonna stop here, and I would be happy to answer the questions or maybe help you with some of your projects that you have going on.